I'd like to work out for you example 8.4 in the book. If you haven't done it already, you should read the statement of the problem carefully and see if you can draw a before and after picture. The problem is about two gliders on an air track that slide toward one another and bounce off one another. You're given something about the initial speeds of the gliders, and you're given the details about the speed of one of the gliders after the collision, and you're asked to calculate how fast the other glider is going. So if you want to pause the video and see if you can draw a before and after picture, that'd be great. Here's what I get. Initially, we have one glider on the left moving to the right, and another glider on the right moving to the left. And over at the sides, I tell you the various things here. The mass of the glider on the left is 0.5 kilograms, and it's moving 2 meters per second to the right. And the glider on the right has a mass of 0.3 kilograms, and it's moving to the left at 2 meters per second. After the collision, you don't know how fast the first glider is moving, the glider on the left, but you do know how fast and in what direction the second glider is moving. And that's again going 2.0 meters per second, but back to the right. So glider B reversed its direction, but its speed stays the same. So in order to do conservation of momentum problems, you have to draw a before and an after picture and make note of all the masses and velocities that you're given. Additionally, we're going to need a coordinate system because momentum is a vector. We need to work with it on a coordinate axis. So I think it makes good sense to call the plus direction to the right. So anything that is pointed to the right, we're going to assign a plus sign, and anything that's pointed to the left, we're going to assign a minus sign. All right, so the way you proceed is to make note of what is the initial momentum, the momentum before the gliders interacted. And that's the momentum of the first one plus the momentum of the second one, glider B. But I want to point out the fact that glider B is moving to the left. So I'm going to take that into account right away, and I end up with an expression that would give me the initial momentum. But what I want to point out is that we're going to put in magnitudes now for those velocities. We're not going to put in plus or minus signs for them because we already took care of the direction. So we're going to write a similar expression for the momentum after the collision. Well, we know that the B glider is moving to the right, but we're unsure about the direction that the A glider is going. So here's a little trick when that happens. Write an expression if you don't know the direction of an object's motion, just make it plus. So it's like you're assuming it's to the right. And then when you solve for it, if you end up getting a minus number, it means that the direction is actually to the left. Now for the other glider, it's moving to the right, so we take care of its momentum just with the plus sign. Now I do want to tell you something. I'm using a slightly different notation than the book uses. The book uses I and F, and all of the letters get laden with a bunch of subscripts. I'm going to use this prime notation, and the prime means after or final. Great. Well, because this system conserves momentum, and it conserves momentum because this is all happening on a frictionless track, there are no external forces, we can start by saying that the change in momentum of the system is zero, and that would be the total momentum of the system. That tells us that the initial momentum has to be equal to the final momentum. And that allows us to equate these two expressions that we got. And then we get an equation, which is a truth, that will allow us to figure out the speed of the glider A after the collision. So really, it's just a matter now of copying over the expressions that we wrote before without making any mistakes. So this equation here is a truth that tells us how the speeds and masses of the gliders need to be related because momentum is conserved. And what's left is to realize that you have numbers for everything in here except for the speed of the second glider after the collision. So we can solve this equation for the speed of the first glider, VA, after the collision. I can do it algebraically and I'll write down the result. You could plug in all the numbers now, but in any case, you should be able to come up with an expression that tells us what the velocity of the first glider after the collision is. I'm sorry that's a little bit dry, but that's what we got. I can take one more step if you want to continue doing algebra, and that would be this. Okay, so it doesn't matter really if you can follow along with all the algebra steps, but you could surely do them with numbers if you like. In any case, we end up with an expression that's pretty easy to solve. So you could plug in numbers here, or if you plug in numbers down up here, you should end up with the same result. And what you end up with is that. The important detail that's a bit masked in the problem as you read it in the book is that when you set this all up, assuming magnitudes for all the velocities and plug in their directions in with plus and minus signs, you end up with a negative number for the speed of the glider after the collision. But that has a very clear interpretation. It means that that glider is moving to the left. So we've used conservation of momentum to predict what will happen when two gliders come together, collide, and move apart. We needed to know something about the speed and direction of one of the gliders after the collision, and we could predict the speed and direction of the second glider after the collision.